Have you ever stopped to think about how your computer finds a website that's on a server maybe halfway across the world? It feels like magic, but it all comes down to a kind of digital mailing address. Today, we're going to pull back the curtain on the system that makes it all possible, IP addressing.
So let's start with the big question, right? We have billions of devices out there. Phones, laptops, servers, heck, even smart refrigerators, all connected to the internet. How in the world do they find each other? How does your request for a cat video find the exact right server out of millions?
In the very, very early days of networks, it was kind of simple. Computers just had names, like Bob's PC or Mainframe 1. But you can probably guess what happened next. As more and more devices came online, trying to keep track of every single name became a total nightmare. The lists were huge, it was chaotic, it just didn't scale. A much smarter system was needed, and fast. And to build that system, we first have to get on the same page as the computers themselves. We need to understand the fundamental language they all speak. See, deep down at their core, computers are actually pretty simple. They only understand one thing: electricity. A signal is either on or it's off. That's it. So we give those two states a number. We use a 1 for on and a 0 for off. This super simple two-digit system is called binary, and it is the bedrock for literally everything we're about to talk about. The easiest way to think about this is with light switches. Imagine one switch. It can be on or off, right? Two options. Now add a second switch. Suddenly, you've got 4 possible combinations. Both off, the first one on, the second one on, or both on. Well, by the time you get to just 8 switches, you can create 256 unique different combinations. That's the incredible power of thinking in twos. Okay, so here's how that's actually structured. Think of those 8 switches, or bits, as 8 slots in a row. Each slot has a permanent value. It starts at 1 on the far right, and then it just doubles each time you move to the left, going all the way up to 128.
So now that we have those basic building blocks, let's actually put them together and build one of the numbers that make up an IP address.
All right, let's say a computer gets a series of little electrical pulses that, in binary, look like this: 11000000. All this really means is that the first 2 switches in our row of 8 are flipped on, and the other 6 are off.
So how do we translate this back into a number that we humans can understand? Well, it's actually just simple addition. We only look at the slots that are turned on. So the first on slot has a value of 128.
And we add to the
value of the next on slot, which is 64.
Which gives us a grand total of
192. And that's it. That's all there is to it. That is how a computer takes a simple string of on-off electrical signals and turns it into a number we recognize.
So what we just did was figure out one of those numbers. A standard IP address, which is called an IPv4 address, is simply 4 of these numbers all strung together. Each one of those 8-bit blocks is called an octet, and its value can be anything from 0, which is all switches off, to 255, which is all 8 switches on.
And this is really the key thing to get. To a computer, the address is just one long, 32-digit string of ones and zeros. But for us, the computer does the heavy lifting. It translates each of those 8-bit octets into a regular number, giving us the much friendlier format that we're all used to seeing.
But wait, there's a little more to it. An IP address isn't just a random set of numbers. It has a hidden structure, a kind of secret code that tells devices how to read it correctly.
Honestly, the best way to think about this is like your home mailing address. Part of the IP address is the network portion. Think of that as your street name. It tells you the general neighborhood where the device lives. The other part is the host address, and that's like your specific house number on that street.
So you might be asking, how does a computer know where the street name ends and the house number begins? Good question. It uses a second companion number called a subnet mask. You can think of it like a stencil or a filter that you lay right over the IP address. It tells the computer, okay, this part here is the network, and this part over here is the specific host.
Let's look at a quick example. Imagine your IP is 192.168.12.2, and it has a subnet mask of 255.255.255.0. Now remember how the number 255 means all 8 bits are turned on? Well, those 255s in the mask are basically shouting at the computer, hey, these first 3 numbers, the 192, the 168, and the 12, that's the network. And the 0, where all the bits are off, says this last number, that's the host. So in this case, the network is 192.168.12, and the unique device or host on that network is number 2. Now, this system was absolutely brilliant. It powered the growth of the internet, but that growth happened at a speed nobody could have ever predicted, and pretty soon it created a massive global crisis.
To put it simply, IPv4 was designed back in an era when computers were these giant expensive things in university basements. No one, and I mean no one, imagined a future where every single person would be walking around with multiple internet-connected gadgets in their pocket. We were just flat out running out of unique addresses to give to everyone.
So, some very clever people came up with a brilliant workaround. They decided to reserve a few specific ranges of IP addresses just for private use. These are the addresses your home Wi-Fi router gives to your phone, your laptop, your smart TV. The genius part is, these addresses can be reused over and over in millions of different homes and offices all over the world because they are strictly forbidden from ever being used on the public internet. This one idea saved a colossal number of public addresses.
Which leaves us with a really fascinating puzzle to end on. The IPv4 system has a hard mathematical limit of about 4.3 billion addresses. That's it. But today, right now, there are well over 15 billion devices connected to the internet. We've seen how private addresses help, but that alone doesn't cover the gap. So, how does that math work? It's a great question to think about.